Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's look at the normal distribution and its properties. The normal distribution is a specific type of probability distribution for a continuous random variable, and many human attributes such as height and weight follow a normal distribution. So what is a continuous random variable, John? I hear you cry. Well, it's a variable whose value is a numerical outcome and is random. And what do you mean by probability distribution, John? Well, this is a graph that describes the likelihood of every possible outcome of a random event. The normal distribution is symmetrical and comes in the shape of a bell, and so it's also known as a bell curve, looking like the one on the whiteboard. The normal distribution is controlled by the mean and standard deviation of the data and is centered about the mean. Its width is controlled by the standard deviation or the dispersion of data about the mean. If the data has a low standard deviation, then the data is more packed or less dispersed about the mean, which results in a steeper curve with less width. While if the standard deviation is high, it means that the data is less packed and therefore more dispersed about the mean, and the curve is flatter and wider. We can say that a random variable x is normally distributed with mean mu and standard deviation sigma using the notation shown here, where x is the continuous random variable. This symbol here means distributed as. The n stands for normal. Greek letter mu is the mean, and Greek letter sigma is the standard deviation. Sigma squared is the variance. The empirical rule, or the 68, 95, 99.7 rule, states that 68% of all outcomes fall within one standard deviation of the mean. So that's one standard deviation either side of the mean, indicated by the pink region on the graph. And that 95% of all outcomes fall within two standard deviations of the mean. So that's two standard deviations either side of the mean, indicated by the pink region. And that 99.7% of all outcomes fall within three standard deviations of the mean. So that's three standard deviations either side of the mean, which is indicated by the pink shaded region on the graph. Now let's look at how the normal distribution applies to some real-world examples. In the first example, let's say we measure the weight of males in a typical workplace. Let's assume the mean value across all the weight measurements is 82 kilograms. Then we might see the distribution look like the bell-shaped curve shown here, where we have the lighter males down at this end of the graph and heavier males at this end of the graph. Let's assume that the standard deviation of the distribution is 5 kilograms. Then we can write this as the random variable x is a normal distribution with mean of 82 kilograms and standard deviation of 5 kilograms. And based on the empirical rule, or the 68, 95, 99.7% rule, 68% of the weights fall within one standard deviation of the mean and equates the area shown in red on the graph. And so 68% of the weights fall within 77 kilograms and 87 kilograms. And 95% of the weights fall within two standard deviations of the mean. So that's 82 kilograms, which is the mean, plus or minus 10 kilograms, which equates to the area shaded in red on the graph, which has weights between 72 kilograms and 92 kilograms. And 99.7% of all weights fall within three standard deviations of the mean. So that's 82 kilograms, which is the mean, plus or minus 15, which equates to the area shaded in red on the graph and has weights between 67 kilograms and 97 kilograms. In this next example, let's assume that x is the random variable of weight of boxes in the middleweight division at weigh-in. And let's assume that this is normally distributed with a mean of 72 kilograms and a standard deviation of 0.3 kilograms. Then we might see the distribution look like the bell curve shown here. Note that this curve is much steeper and not as wide as the previous curve. This is because it has a much smaller standard deviation. So we can write this as random variable x is normally distributed with a mean of 72 and a standard deviation of 0.3. The lighter boxes would appear at this end of the curve, and the heavier boxes would appear at this end of the curve. And based on the empirical rule, or the 68, 95, 99.7% rule, 68% of the weights would fall within one standard deviation of the mean. So that's 72 kilograms, which is the mean, plus or minus 0.3 kilograms, which is the standard deviation. And these weights are represented by the red shaded region on the graph. And therefore, 68% of the weights fall between 71.7 kilograms and 72.3 kilograms. And 95% of the box's weights will be within two standard deviations of the mean. So that's 72 kilograms, which is the mean, plus or minus 0.6 kilograms, and is represented by the area shaded in red on the graph. And 99.7% of the box's weights fall within three standard deviations of the mean. So that's 72 kilograms, which is the mean, plus or minus 0.9 kilograms. And that's the area represented by the red shaded region, where the weights are between 71.1 kilograms and 72.9 kilograms.